Well, hello everyone, and welcome back to Things Made Simple. Today, we're going to be adding velocity sensitivity to our YM3812 module. You'd think this would be a pretty simple process, but there's some quirks that make this a little trickier than you'd imagine. So, what is velocity sensitivity, and why do they call it that? Well, in order to add expressiveness to your playing, you want to be able to control the volume of a note by how hard you press the note on a keyboard or maybe a pad on a sequencer. And while there are lots of fancy tricks today to measure pressure, early touch-sensitive keyboards had to approximate that pressure by measuring how quickly you press the key. Here's a crude animation, but let's just go with it. Pretend that this is the side view of a key on the keyboard. As you press it, the key closes a switch. And then when you've completely pressed the key, it closes a second switch. The keyboard uses the time difference between those two switches to calculate how fast you've pressed the key. Now, the more force you use to press the key, the faster it's going to go down. But again, we're really only measuring the speed or the velocity of the key, not the pressure directly. There are keyboards, of course, that do measure pressure, and they provide things like aftertouch, but that's a whole different topic, also a very cool topic. Anyway, this is why they call the attribute velocity. And it turns out that the velocity attribute has been with us the whole time. Whenever we detect a note press, our note on handler function gets called, and velocity is one of the arguments that gets passed along with it. Up until now, we've just kind of ignored this, but today we're actually going to use it to change how loud the note plays. Cool, so how do we determine how loud a note plays? Well, looking at our patch properties, we have this property here called level, and that's going to change the amplitude of an operator's waveform. But we also have these other three properties called level as well, one for each operator. So do we want to adjust all of them? Well, that's the first question we need to answer. If you recall from all the way back in the first video, the YM3812 supports two different ways of combining operators, frequency modulation and mixing. In the case of frequency modulation, you've got one operator that modulates a carrier operator. Whereas in mixing, you treat the modulator like another carrier and just mix the two sounds together. Any operator that works like a carrier is going to directly impact how loud a note sounds, but modulator operators are going to change the timbre or brightness of the sound instead. So let's set up a quick truth table to see which levels we need to scale based on velocity. In most cases, we want to scale. But if we're dealing with operator 0 of algorithm 0, or better said, the modulator operator of a frequency modulation algorithm, then we don't want to scale it. In code form, it looks something like this. If the algorithm is 0 and the operator is 0, don't scale. Instead, do what we do today and just grab the level from the patch data. Otherwise, we need to scale the level based on the velocity of the key press. And that leads us to our next question. How do we combine level and velocity? Velocity, like most values that get transmitted over MIDI, ranges from 0 to 127, where 0 is the softest and 127 is the loudest. And we want to use this as a fraction of its highest value, or 127, so that we can then scale the level. Now, level comes from our generic patch definition, so it's also going to range from 0 to 127. And to help us visualize things, let's try plotting different combinations of velocity and level to see what our scaled level looks like. We'll put different levels across the top and different velocities along the left, and then we'll use our formula to calculate scale levels for all of the different combinations. As you can see, the highest number is here in the top right, and that makes sense because that's where velocity and level are both the highest. And from there, as we move either velocity towards 0 or level towards 0, then the scaled velocity is going to approach 0 as well. And this would normally make sense too, but there is one issue. According to Yamaha, 0 is the loudest value of level, not 127. That means that the top left corner of the table should be the loudest corner, not the top right, and then the scale levels should diminish as they get closer to the other three corners. Also on the YM3812, level is a 6-bit number, so the maximum value you can have is 63, not 127. So we're going to need to not only flip this table around, but we're also going to have to divide everything by 2. Going back to our formula, let's first take care of the divide by 2 issue. We're going to swap 127 with 256, and that's going to give us the appropriate range. Now, to invert the x-axis, we're going to subtract level from its largest value, which is 127. This way, as level increases, scaled level will decrease. Okay, let's plot this out again. Beautiful. The values are now coming out of the top left corner, and our highest scale level is now 63. But of course, there's one more issue. Remember, the YM3812 expects that the loudest value is 0, not 63? Right now, the top left corner is the quietest, and all of the other corners are the loudest. So we actually need to invert this entire table. That's simple enough though. We just subtract the entire formula from 63. And there you go. Our loudest value has a velocity of 127 and a level of 0. But then as you get further away from those values, things get quieter. Now let's see how this manifests as code. We're storing our scaled level in this op level variable. Our 63 minus flows down, as does the 127 minus level, but we're going to replace level with a reference to the level property of the patch. Similarly, we're going to replace velocity with a velocity value that's stored in the channel states array. We're going to talk about that more in a minute. Finally, we divide by 256. But to do that, we're going to use a trick. Whenever you're dividing by a power of 2, it's significantly cheaper to right shift by the power of 2 as opposed to dividing by the number. In this case, 256 is 2 to the power of 8, so we can right shift by 8 bits. But there's a second part of that trick. Since we're dealing with integers and not decimals, we need to make sure that we multiply level and velocity before we divide by 256. Think about it like this. If we were to right shift velocity first, then we're taking an 8-bit number and we're right shifting it by 8 bits. That's always going to be a 0. So we're then going to multiply level by 0, and that's also always going to be a 0. But if we multiply by level and velocity first, then we can get a much larger value than 256, and so right shifting by 8 bits is still going to produce a meaningful value. All that to say, this is why this piece of the formula gets wrapped in parentheses. Okay, let's bring back the other code and put the pieces together. Beautiful. This is the code we need to scale level. And that begs the next question. Where do we put it? Well, there are actually a few changes that we need to make. So let's trace how the signal flows through our program and go through and make the changes. Our story begins in the main.ino program file with our note handler function. That function receives the note information and then calls the patch note on function in the YM3812 class to tell the class to play the note. As of now, the note on handler function only passes the MIDI note and the patch to play, but we need to update it to pass the velocity as well. So let's go ahead and do that. Here's our handle note on function. And as you can see, velocity is already being passed into this function. We just need to pass it on to the patch note on function. And there's two different cases where we do this, depending on whether this is a percussion sound or an instrument sound. Next, the patch note on function figures out which of the YM3812 channels to use, and then saves all of the meta information about the note we're playing into the channel states array. So we're going to have to include velocity as one of those meta pieces of information. So let's go ahead and update patch note on, starting with the function definition that's in the YM3812. This is pretty simple. We just want to add an integer for velocity. But remember, there's also a second version of the patch note on function, and we have to update that one too. This version's used for percussion sounds, and it extracts the note number of the patch before calling the regular version of patch note on. All we're going to do is add the argument velocity and then pass it on when it calls patch note on. Okay, let's take a look at the implementation of patch note on now. This receives the velocity and then just saves it into the channel states array. Channel states is made up of a bunch of YM channel structures, so for that to work, we're going to have to update that structure to include a velocity property. And that's pretty straightforward too. I went with the default here of 127 so that the note would always be fully on by default. But realistically, it's going to get overwritten anyway, so it's kind of academic. After updating the channel states array, our patch note on function is going to call channel play note. And then as part of playing a note, this function is going to update the patch information in the YM3812 by calling the channel send patch function. This function is where all of the magic happens, and we take a generic patch and translate it into the settings for the YM3812. And because it sits inside of our YM3812 class, it's also going to have access to the channel states array, and thus the velocity for the note. So this is where we're going to insert that code that we wrote earlier. I know it's a lot of code, but don't freak out. If you watched episode 6, then you've actually seen all of this code already. And if you haven't, I'll leave a link here. Go watch that because there's a ton of context for how this function works in there. Realistically, there's only a few things that we need to change in here. First, we're going to add op level as a temporary variable to store our scale level as we calculate it. Then, inside of our loop, we're going to drop in that code that we wrote earlier. It calculates the scale level based on the level in the patch and the velocity that we saved in the channel states array. Finally, when we send the data up to the YM3812, we need to swap in the scale level that we calculated instead of pulling the level out of the patch. And guess what? That's it. Those are all the changes we need to make. It's demo time. Let's try playing a couple notes on the keyboard and see what happens as we hit them harder. Notice how the timbre of the note stays the same even as the note gets louder or softer. Here's a bass patch. Notice how you can kind of hear a pluck in the string even at low levels. One more, this is just white noise, but notice how it stays white noise at all levels. Okay, just for funsies, what happens if we scale every operator, including the modulator operator? Let's go ahead and comment out the if statements. We'll compile this and send it up to the module. Okay, see how the harder you press the note, the more twang you get? I don't know, there might be something to this, especially for plucked string instruments like a bass. And this string patch gets brighter as you press the note harder. This waveform is interesting because you can really see on the oscilloscope how the edges of the wave get sharper the harder you press the note. If you look at the same patch without scaling the modulator, the edges stay sharp even at lower levels. This next patch is white noise, but you wouldn't know it until you press the note hard enough. Clearly, scaling the modulator operator does more than change the volume. It fundamentally changes the sound. But who knows, there may be situations where that makes sense, like a bass string that gets pluckier the harder you pull it. But if you're just trying to change the volume of the sound, then you're going to want to stick to those carrier operators and only adjust those levels. Well, with that, I think we're going to wrap things up for today. As always, the code's available on GitHub, and I've written everything up in an article on my blog, Things Made Simple. If you enjoyed this video and you think others might find it useful too, give it a thumbs up. It really helps out the algorithm. Thank you so much for watching, and we'll see you next time on Things Made Simple.